Welcome everyone to our data science and computational statistics seminar. It's my great pleasure to introduce our speaker today, Yulong Lu. He currently assistant professor at Department of Mathematics and Statistics at University of Massachusetts at Amherst. Yulong finished his PhD in 2017 at University of Warwick. And from 2017 to 2020, he was a research assistant professor at Duke University. So today he will talk about approximation and generation of two-layer neural network for solving high-dimensional PDEs. We will record our lectures, and later on we will upload to the YouTube channel Birmingham Mathematics. So thank you very much. And if you have any question, you can either just simply unmute yourself to ask, or you can type in the chat box. So please welcome Yulong.
Thank you. Thanks very much for the invitation and for the introduction. It's my great pleasure to give this talk online. I just talked with home and other people that I've been to Birmingham many times, but I never got a chance to visit University of Birmingham. So it's I'm happy to be here to talk with people over there. I hope everyone is staying safe and healthy. So I'm going to talk about some recent theoretical work on neural network methods for solving high-dimensional PDEs. So this is based on a series of work, collaboration with Zhang Chen, Jianfeng Lu, Ming Wang, and they are both from they are all from Duke University. So I want to have more interactions with the audience. So if you have questions, please unmute yourself and feel free to ask questions. So since I'm going to talk about PDEs in high-dimensional space, first I will start with a few motivational examples where you see a high-dimensional could arise, high-dimensional PDEs could arise. The first example I want to mention is the Schrodinger equation in quantum physics. So as we know that the Schrodinger equation describes the evolution or the states of the wave function in a quantum system. On the right side of the image, you will see a time-independent Schrodinger equation, or the so-called eigenvalue problem of the Schrodinger operator. So in the equation, this H hat is a Schrodinger operator, the Hamiltonian operator, and the E is the energy level. Psi is a solution of the equation which describes a wave function. So this equation is a high-dimensional PDE because the wave function is a function of the positions of the electrons in a quantum system. So the number of electrons can be huge in a system. So then the psi is going to be a function of high-dimensional variables. So here I'm only considering the eigenvalue problem or time-independent problem, but in principle you can generalize. You could also consider the evolution of the wave function by solving the time-dependent Schrodinger equation. So that's the first example of high-dimensional PDE from physics. So the second example comes from quantitative finance. It's about the option pricing in quantitative finance. So probably the most famous model is the so-called Black-Scholes equation for pricing, option pricing. It's a PDE. It's a second-order degenerate parabolic PDE. The solution of the PDE describes the price of option. It's usually a function of time and also the function of the prices of the stock assets in the market. So as you see, the V is the solution of the PDE. It's a price of the option, and the V depends on time and depends on S, which is the prices of the stock assets. Okay. So the number of assets in the market usually range from hundreds of thousands. So then the V is going to be a function of high-dimensional variable as well. Okay, so that's another example. You'll see the high dimensionality arises. Okay. So that's these two PDEs coming from physics and finance. The last example I want to mention is the so-called reinforcement learning. It's a machine learning method for solving problems in game theory. Okay. So the basic idea or the goal here is try to learn how to make decisions in order to maximize certain rewards. So usually the problem can be formulated as a stochastic control problem, where you are trying to optimize certain or maximize certain expected loss or expected rewards over certain control sets. Okay, so the number of controls or the number of the cardinality of the decision sets is usually very large. So the control problem is really defining a high-dimensional space. And a typical way to solve this stochastic control problem is to use PDE method, in particular the Hamiltonian-Jacobi-Bellman equation, right, to solve for the value function, so optimal value function. And since the control variable is lying in high-dimensional space, then the PDE is really defining a high-dimensional space as well. Okay, so this is another PDE you could imagine that comes from the reinforcement learning problem. Okay, so that's three examples. Well, in all of these problems, the goal is trying to approximate the solution of the PDEs defining a high-dimensional space. Solving these problems in high-dimensional space is really challenging because many traditional numerical methods, such as finite difference methods or finite element methods, they both suffer from the curse of dimensionality, which means that the computational cost can grow exponentially fast as the dimension increases. Okay. For example, a typical error estimate for those methods in solving these PDEs look like the following. So some kind of norm between the true solution and the numerical solution is bounded by an edge to the alpha, where the edge is the mesh size of the numerical scheme, and alpha is really positive and depends on regularity of the solution, and also depends on the the degree of polynomials you used in the approximation. And in a d-dimensional space, you see that the mesh size edge is roughly like m to the minus d, where m denotes the degree of freedom of the methods or the number of parameters in the numerical methods. For example, in the linear, if you solve linear PDEs, then typically you will get a linear system in the end, finite dimensional linear system in the end, while the m will be the size of the linear matrix in the end. Okay, so as you can see that if you plug in the h into the error estimate, you will get the error between the true solution and the numerical solution is bounded by m to the minus alpha divided by d. Okay, so there's a 1 over d in the convergence rate, right, in terms of the degree of freedom. So this 1 over d convergence rate refers to the curse of dimensionality. So then the question for us would be, can we do better if we use different methods, such as the neural network-based machine learning methods? So that's the question I want to ask in this talk. Okay. So recently there have been many different kinds of numerical-based methods for solving PDEs. Here I'm showing an incomplete list of some of them. I forgot. I have to apologize if I missed any references, any work from the audience. But the first method is based on the kind of a stochastic formulation of some class of PDEs, in particular parabolic PDEs. There's a method called Bsd Methods. Bsd refers backward stochastic differential equation. So the basic idea is trying to design certain loss function, which is trying to match the stochastic formulation of the PDE with a neural network-based formulation. Essentially, are parameterizing the coefficients or the solutions, the quantity of the processes using neural networks, and you're trying to matching the both quantities using certain loss functions. And the idea based on this is will give you the deep BSD method. This method is very efficient for solving certain kind of PDEs, like parabolic PDEs or certain non-parabolic PDEs. But I have to say that this idea cannot be generalized to other type of PDEs if the PDE does not have the stochastic formulation. Okay, it strongly relies on the probabilistic interpretation of the equation. Okay. The second class of method is based on minimizing the least square loss or the square misfit of the equation. So the couple of methods based on this idea, like physics-informed neural network methods or pins proposed by Kanedakis, and deep Galagi method DGM, and also SelectNet. Okay. So there are a couple of other methods based on this idea. I'm not going to list all of them, but the basic idea is you're trying to parameterize the solution of the PDE using neural networks, and then you create a loss function by just taking the L2 error between the operator acting on the solution, the PD operator acting on the solution and the right hand side. Okay, and also sometimes you have to include the boundary conditions as well. Okay, so that's essentially trying to build at least a square loss from a PDE. Okay. And the third class of method is based on a similar idea, but they're using different loss function. So the loss is based on the Ritz formulation of the equation. The idea based on this method is called Deprived Method, proposed by Weinan and his student in 2017. And later on, I will mainly focus on the analysis on this method. But our idea can be, our tools can be generalized to analyze other type of methods as well. So the first class of method is based on a different loss. It relies on a Gallagian or weak formulation of the PDE. And this method is called weak adversary network. So the kind of the second up to fourth item based on the similar idea, trying to minimize the loss based on the PDE, and the loss are essentially based on different formulation of the equation. And I want to also mention the last type of method. It's based on learning the solution operator. So in the first four items, the goal is trying to learn the solution for a given initial condition or given boundary condition. But the last, the final method is based on is trying to learn the solution map, or trying to learn the solution of a class of equations with different initial conditions or different boundary conditions. Okay, so the two types of methods for doing this, one is deep ONet, proposed by a group of Kanedakis, and the Fourier neural operator. Okay. So the last method is slightly different. It's more ambitious. It's trying to learn the operator. And the first four methods is just to learn the one solution given one specific initial condition or boundary condition. So as I said, I'll mainly focus on the Ritz formulation based methods called deep Ritz methods in this talk. But I'll mention some later on that the ideas can be generalized to other methods as well. So numerical analysis. So all the methods I mentioned before, there are very little numerical analysis on that, and most analysis are focused on pins. So for example, there's some recent work by a group of Kanedakis and Mishira Molinaro. They did some kind of a posterior and a priori error analysis for the pins. However, I have to say that those error estimates do not capture the effect high dimensionality, which means that the error estimates do not have dimension dependence in the results. So, and the main question for me is to get some kind of dimension-free error estimate for the neural network-based methods. Okay, I will do this for the Deprived method. Of course, a complete mathematical theory is still missing for this question, but I'll mainly focus on the approximation and generalization error in this talk for the Deprived method. Okay. So since I'm going to talk about numerical analysis of the neural-based methods, so I want to give a very quick recap on the recipe of a traditional numerical analysis of PDEs. Okay. So in a traditional numerical analysis, a very important ingredient in the analysis is a function space of the PDEs. In most cases, we'll talk about subleft spaces or Holder spaces in the traditional numerical methods. And based on that, we have regularity theory of PDEs in those spaces. For example, for elliptic PDEs, you in subleft spaces, you really have the subleft HS plus 2 norm of the solution is bounded by the HS norm of the right-hand side. So basically, you improve the regularity by 2, right, in the subleft case or in the Holder case. And with this regularity, you can actually build an approximation theory for the solution. In the finite element case, we usually use a piecewise polynomials to approximate a solution. So you really get the optimal approximation for the solution scales like the following. So you have the h to the alpha as the approximation error, where the h is the mesh size of the method, finite element method. So that's a local approximation result. If you want, you can approximate any h or sublevel functions by using a piecewise polynomials. And after you get the approximation theory, you also need some kind of stability result. Okay. So the stability estimate, which allows you to transfer the approximation error to the error of the final discrete solution. So in the finite element method, this was done usually by CR's lemma, which says that there's some kind of stability in the numerical discretization. So the error between the solution and the finite element solution is bounded by the optimal approximation or the local approximation of the polynomial to the solution. Okay, so this usually done by the CR's lemma. By combining these two, but the local consistency results and the stability, you basically get the final estimate, right? So the final error estimate will be also h to the alpha, scale like h to the alpha in the end. So I want to recap those ingredients in the analysis, because later on, when I discuss the numerical analysis for neural network methods, we basically do the same thing. So we will redefine a new function space, a primitive function space that are tailored to or tied to the neural networks. And also we define regularity theory of the PDEs in the new space, and as well as function approximation theory, and also stability results in this in the neural network setting. Okay. So all the 4 ingredients will be there, but we are going to replace some using in the setting of neural networks. Okay. So I'm going to focus on 2 simple model problems. A simple domain, omega is going to be a hypercube, a d-dimensional hypercube, 0 to the d. The first class of problem I will focus on is a stationary Schrodinger equation with a Neumann boundary condition. So there are 2 parameters in the equation. The function v is a potential function, and the function f is a source term on the right side. Okay. So I'll focus on the Neumann boundary condition because later on we'll use the deep Ritz formulation or the Ritz formulation. So the energy functional event will not involve any terms on the boundary. So this is probably the simplest way to get rid of boundary condition. So I'll focus on the approximation of the solution in the interior of the domain. Okay. Another class of equation, another class of problem is the Neumann eigenvalue problem of the Schrodinger operator. Okay, so this we're looking for the eigenvalues and eigenvectors to the Schrodinger operator minus Laplace plus v. Okay. And I'll focus on computing the ground state u0 that corresponds to the minimum eigenvalue lambda 0. Okay. At the moment, we think the idea can be generalized to solve to find approximation result for all the eigenfunctions. But there's still some additional work to be done. Okay. So I'll focus on the ground state computation at the moment. So the idea of Deprived method is based on the Ritz formulation of the PDEs. So the idea is that the solution of the PDE or the solution of PDE problem can be formulated as the minimizer of certain energy functional. So for the stationary Schrodinger equation, you can easily can be easily checked that the solution is actually the minimizer of this energy functional. So the energy I wrote on the right hand side, it's somehow the sum of the kinetic energy and the potential energy subtract the source term, the integral of the source term. For the eigenvalue problem, the ground state also satisfies the variational principle. So it's also given by the minimizer of the Rayleigh quotient. Okay, so it's like the total energy divided by the L2 energy. Okay. So then the idea of the Deprived method is, okay, so in the two displays, we're trying to minimize its energy within the H1 space, and the Deprived method is to somehow relax the bigger space. So it's to solve the energy, to minimize the energy within the smaller class of functions defined by neural networks. Okay, so I denote by FM. Well, of course, the FM is a subset of H1. Okay? So M is usually the complexity parameter of the network. I will define later. In this talk, I will focus on the FM defined by a set of two-layer networks. Okay, so the typical function of a two-layer network is the following. So it's a constant plus a linear combination of the ridge function, okay, with weights gamma I, and the Wi and Bi, the parameter is in the weight function, in the ridge function. So all the total parameters are the C, gamma I, Wi, and Bi. Okay. The M is the number of neurons in the hidden layer, or in this two-layer network. Okay. All right, so that's a setup. So then as you see that to compute the U0 or U star or the approximation of them, we need to evaluate the energy functional. Okay, so this usually involves a high dimensional integral. So if the omega is 0, 1 to the d, then this is really a d-dimensional integral, 0, 1 to the d. So evaluating this integral is very challenging. So what people usually do is to use a Monte Carlo approximation of the integration. So what you do is you approximate the integral with a finite sum or empirical sum of the test function evaluated at certain sample points. So here I'm showing the naive the Monte Carlo scheme where the xj are the uniform random variables on the omega, and then in that case you can write the approximation of Monte Carlo scheme for the energy, these two energies, as the following. So the first one is the finite sum of this discrete energy, if you want, and in the second case you have the ratio of these two discrete energies. Okay, so that's reducing the population loss into the empirical loss by replacing the high dimension integral with this empirical sum, and then we can get a discrete problem. So this U and M will be the minimizer of this discrete energy. Okay, so here remember that two parameters. So N is a number of sample points in the Monte Carlo scheme. M is the number of hidden layers in my neural networks. So M denotes the complexity of the model, N is the sample size. Okay. So the question, a major question for us is how well can the discrete solution approximate the true solution when the D is huge. Okay. So as I said, or to answer this question, or to give a numerical analysis of the approximation scheme, I want to have these four ingredients as I did in the standard numerical analysis. So the first ingredient is a function space. So standard functions numerical analysis relies on sublength for Holder spaces. But it turns out approximating functions in high-dimensional space, the regularity is somehow not that essential, or it's too kind of broad, or too it's not precise enough, okay, to give the to discuss the functions in high-dimensional space, because this sublet space or Holder space are too complex in some sense. So instead, we need some kind of low complexity of functions to discuss neural network approximation. So there are certain results, previous results in this direction, where the sublet spaces and sublet or Holder functions are too complex, which means that approximating these functions using neural networks will suffer from the curse of dimensionality. So this was proved by the initial two papers by Yarotsky, and later on, this was also revealed by other two authors, This suggests that this we cannot gain that much using neural networks to approximate sublet or Holder spaces in high-dimensional space, because they all suffer from the curse of dimensionality. So then what kind of functions can we gain better, right, by using neural network approximation? Or in that case, in other words, what functions will have low complexity? Okay, so the answer to this question was first studied by Andrew Barron in 1993. He proved that if a function f satisfies the weighted L1 norm of the Fourier transform of the function is bounded, so the CF, if the CF is bounded, then there exists two-layer networks Fn with the unhidden neurons and with sigmoid activation function, such that the L2 difference between the two function and the neural network approximation is bounded by the CF times n to the -1/2. Okay, as you see, that's the approximation rate is always 1/2 or -1/2. It doesn't depend on the dimension of the function. Okay, as long as the CF is finite. Okay. So this is the first approximation result, where you see the approximation is independent dimension for class of functions. There's another class of functions which is which I will also call Baron space or Baron functions. It's defined by in the paper by Weinan and his collaborators. So it consists of functions of the following form. It says a function can be written as a kind of a ridge function with a ReLU activation function integrated against the probability measure rho on the parameter space. Okay, A, B, C are the parameters of the ridge function, and you integrate this function against the measure. Okay, if the function f satisfies the so-called Baron norm of the function, which is defined by the expected L1 norm of the parameters over all the possible probability measures is finite, then this L2 difference between these two functions is also bounded by Baron norm times n to the -1/2. Okay, so you get similar results, approximation results as before, but these two function spaces are slightly different. In the first case, Baron defined the function space using Fourier transform. So sometimes I will refer this as a spectrum Baron space because it relies on the spectral information of the function. In the second case, it defines the function class using integral formulation. So basically, the function can be written as an integral of this ridge function against a probability measure. So in these two cases, somehow the spaces are not so convenient to be used as a function space for PDEs. The reason is that in the first case, in the initial definition of Baron, the function space has to define on the whole space in order to define the Fourier transform. If the PDEs defined on bounded domain, the solution will be defined on the bounded domain. So you have to find a way to extend the function on the whole space so that the extended function will satisfy this constraint. And finding a good function space which satisfies this extension property is difficult. It's not easy to show how to characterize the function space satisfying this constraint. In the second case, in the Wiener's definition, although the function can be defined on the bounded domain, it's hard to show that the solution of PDE will take this integral form. It's typically not easy to show that the function can be written in this the integral of this ridge function against a polar measure. Although there has been some recent work that by Wiener his collaborator that they show that for some simple PDEs like PDE equation or simple Hamilton-Jacobi equation, the solution indeed belongs to this notion of Barron space. But for in general, for all the PDEs, for example, the Schrodinger equation, it's not easy to show that the solution is indeed in this space. Okay, so for PDE problems, we really need a low complexity space that are tailored to PDEs. Okay, so in this talk, I will define a new spectral Barron space motivated by Barron's initial definition. On the whole space, I'm going to define the Barron space on the hypercube 0, 1 to the d by using the eigen expansion, or in particular cosine expansion, instead of the Fourier transform. So I will denote the U hat to be the expansion of the expansion coefficient of the function in L2 with respect to the cosine basis. So it's basically the product of the cosine functions in each coordinates. So I will define a spectrum Barron space on omega as a subset of L1 space, such that the cosine expansion coefficient belongs to the weighted L1 space, with a weight given by 1 plus pi to the s times k, the L1 norm of k to the s. So the k is a index for the expansion coefficients, and this k subscript L1 is L1 norm of the vector k. Okay. So there's an index s is the index for the Barron space. Okay, so we mainly consider s bigger than 0. There's a remark about this space. So you see that the Barron space can be viewed as a width L1 space on the coefficients on the lattice. While if you write down the Sobolev space, the standard Sobolev space HS, in terms of the full cosine expansion, it's going to be a weighted L2 space on the lattice. Although the weights is slightly different as well. So the weights will be like 1 plus pi to the s, pi to the 2s. In fact, if you write HS space, pi to the 2s and k to the 2s, 2 norm of k to the 2s instead of 1 norm. But the key difference is that the Barron space is weighted L1 norm, L1 space on the coefficients, but the Sobolev space is weighted L2 space on the coefficients. Okay, so the moving from L2 to L1 will give you a lot of benefits in the end. As you will see in a second, I will state approximation results for functions in this space. You will not get the curse of dimensionality in approximation. Okay. So that's a great benefits from moving L2 to L1 to L1. But you can also show that B2S is embedded to HS. Sorry, B2S is embedded to HS for any s bigger than 0. Okay, so the first result I want to mention is the approximation. As I talked before, that for finite methods, we have a local approximation by using polynomials, piecewise polynomials. Here we're using the neural networks to approximate Barron functions. So let's consider approximation of the I'll call it B omega is a short notation for B2. Okay, this Barron space with index 2. The reason why I use B2 is because, as I just showed you, that the B2 is actually embedded to H1. Okay, so H1 is a minimum regularity, which is required to define the energy functional in these two equations, second order equations. So let's consider approximation of this Barron functions using two-layer networks. In particular, I will define as parameters B. Okay, so capital B is somehow the magnitude of the parameters, okay, in this network. and the phi is activation function. So I will later on will specify what activation function I'm going to use. So basically, B controls the parameters of the C and the sum of the weights gamma I. Okay. So that's the function class we're going to use. The first result is for the ReLU network. We can show that there exists two-layer networks with a ReLU activation function with M hidden layers, hidden neurons, with a B given by the barrel norm of the function, such that the H1 error between the neural network and the solution U in the B2 is bounded by a constant times barrel norm of U divided by M to the square root of M. Okay. As you can see, the convergence rating of M is independent dimension. It's always one half or minus one half. This result is similar to the result proved by Baron and Winan and his collaborators, so that you get the independent dimension convergence rate in the error estimate. So there's a drawback about this result, because ReLU is not smooth enough. ReLU only has one derivative. You can take only one derivative in ReLU, then you get this piecewise constant. However, this is enough to define energy functional because this is a H1 space, H1 function. However, in practice, you have to take another derivative on the energy functional or the empirical energy functional, empirical loss function, in order to train the network. Okay, so somehow you need at least two derivatives to run the gradient descent or stochastic gradient descent in the training process. So next, what I'm going to do, I want to replace the ReLU function by a smooth activation function, so that you can take any derivatives on the loss function. Okay. So I'm going to replace the ReLU by this approximation. It's a software plus function, or rescaled software plus function. So denoted by SPZ, it's a rescaled log of 1 plus e to the z. Okay. As you can see, that the software plus is an approximation to ReLU when the scaling parameter is large. Okay. So you can get a similar result as before, but the only difference is that the error bound, in the error bound, you get an additional prefactor in the numerator, where the numerator only depends on the log of M. So you pay additional penalty on replacing the ReLU by the software plus, because you introduce this scaling parameter tau. You get the additional factor, log factor, in front of approximation results. Okay. So I would say that the both approximation rates are given by square root of M. However, this rate may not be optimal. Okay, so you can actually get sharper rates. It's given by 1/2 plus a constant divided by D. If you use other activation functions, for example, K. This has been proved in recent two papers by Siegel and Xu. However, I would say that the improvement is tiny when D is large. So it's alpha divided by D, and then the alpha is actually depends on the exponent in ReLU K, depends on the K in the result. Okay, so that's about approximation. So for the Baron functions, we can construct a two-layer network to approximate Baron functions with a rate which is independent of dimensionality. Okay. So next, with the approximation results, I can state the main theorem for the generalization error for these two problems defined earlier. Let's assume that the true solution of the PDE is a Baron function with index 2, and U and M will be the discrete solution of the empirical laws within this two-layer network function space with a rescale software plus activation function. Okay. So I'll choose a special scaling in this rescaled activation function, so the tau will be always root M. Okay. It turns out this actually gives a good trade-off between the different terms in the approximation. Okay. So then the final generalization error in terms of energy difference is the following. So the expected energy difference between this energy evaluated the discrete solution and the true solution is bounded by a sum of two terms. Okay, the first term is actually coming from the Monte Carlo integration, the error in the Monte Carlo integration. So that's why I have a 1 over square root of n. That's a typical error in the Monte Carlo scheme. And the second term is the approximation error. So you have a log squared of m divided by m. Okay. So I have to mention that it's important that the first term, in the first term, there's a numerator in the first term. That's like the square root of m times log m squared. So this term comes from, so as you can see, the increasing with respect to m. So if m is large, which means that the numerator gets more and more complex. So somehow the function space becomes larger and larger. So you have the Monte Carlo error is going to be large if the function space is too large. So if you want this numerator part is basically somehow the variance of the Monte Carlo scheme, if you want. It plays a role of the variance. And I have to emphasize that C1 and C2, they are constants depending on the Baron norm of the true solution and the dimensionality, but they only depend on these two quantities at most polynomially. So there's no cursive dimensionality in these constants. Okay. And if you trade off these two terms, these two error terms, you get optimal scaling for the number of hidden neurons. The m will be optimal choice for m will be n to the 1/3. Okay, so in this case, you get the final error estimate in terms of the sample size is going to be log n divided by n to the 1/3. Okay, again, this rate 1/3 is independent of dimension. Okay. Any questions about this result before I move on? Okay. If no question, I will move to the next result. So as I said previously in the classical numerical methods, we also need a stability to transfer the local approximation to the final error for the discrete solution. In the previous result, I see the result for the energy difference. Okay, so can we get the error in terms of the comparing can we compare the error between the solution and the discrete solution itself? So this is what the stability results is doing. So for any, we can prove that for any H1 functions, it turns out that the energy difference is actually equivalent to the H1 or squared of H1 between the difference of the two functions U and U star. Right? With these results and the previous generalization error for the energy difference, you can write the generalization error estimate for the H1 difference of the between the true solution and the discrete solution. Okay, so that's for the stationary Schrodinger equation. And next result is for the generalization error of the ground state of the Schrodinger operator. So in this case, our goal is trying to find a solution of the function U0 or the ground state. So here I normalize the ground state because in general ground states are not unique. It's only unique up to normalization. So let's assume that it's normalized. And again, I have this discrete solution U and M. Okay, so then we'll also assume that U and M is also normalized, and because you can see that the empirical loss is actually a ratio between these two energies. So it's actually only defined up to a constant as well. Okay. So then we can prove that with a high probability, the error between the difference between the energy difference is bounded by the two terms, and these two terms look similar to the previous two terms, but there's only one difference, that on the approximation side, there's only a square of m. Okay, so the previous you have a log squared divided by n. Okay, so this is like a square root of the previous approximation error. Okay? And because of this difference, the optimal scaling for the m will be different, slightly different. So previously we have n to the 1/3. So here we have n to the 1/2 in this approximation. So then if you plug in, then the final error estimate for the energy difference is going to be log n divided by n to the 1/4. Okay. Again, this weight is the independent dimension. Okay, so then that's the error estimate for the energy difference. As I said, we also need some kind of stability to transfer the energy in terms the error in terms of energy difference to the solution itself. So here we have to assume something further. We assume the H has a spectrum gap. So there's a lambda 1 is bigger than lambda 0. Then you can actually control the orthogonal projection of the solution along the direction, all the direction except the eigen direction or eigen state. Or in other words, it's orthogonal complement of the projection operator along the eigen state will satisfy this following bound. So P per U, the H1 norm of P per U, is bounded by some constant times the energy difference between the solution and the ground energy. So then with this result, you can transfer the previous result for energy difference to the orthogonal projection of the discrete solution. Okay, so I'm not going to repeat the results. It's basically the same results for the energy for the H1 norm. Okay, so in all of these results, in these two main results, I assumed that the solution is in the Barron space with index 2. Okay, so that's a big assumption as we made in the typical numerical analysis. We assume that the solution is in Barron space, in Sobolev space. Here we assume the solution is in Barron space. So then the question is, can we verify this assumption? Like, can we prove some kind of regularity theory? Here we refer this as a complexity theory for the PDE. It turns out the answer is yes for the Schrodinger equation or the ground state problem. So for the stationary Schrodinger equation, we have the following result. So if the right-hand side and the potential function are both in the Barron space with index 2, and if the potential has a strictly positive, then you can prove that there's the Bs plus 2 norm of the true solution is bounded by a constant times the Bs norm of the right-hand side, where the constant only depends on the Bs norm of the potential function. And for the eigenvalue problem, we prove a similar thing for the ground state. So if you assume that the potential function is in Bs, then the ground state is actually in Bs plus 2 as well. So in both results, we somehow improve the regularity by 2. So I have to say that the proof for these two results are different, very different from the standard regularity proof, Sobolev regularity results for the PDEs, which usually relies on bootstrapping arguments, bootstrapping the derivatives of the estimate for the weak derivatives. But for these two results, you somehow need more. The arguments is more functional analytic. The first result we use Fedhelm theory to prove this stability result. In the second result, we actually use some kind of fixed point arguments to get the solution is in Bs plus 2. It's not based on bootstrapping the weak derivative estimates. So as I said, these two results are for the Schrodinger equations of the ground state problems. Can we actually extend the results for regularity results for other class of PDEs, right, in the Barron space? The answer is unclear now, so it's a still open problem how to extend this theory to other class of PDEs. However, we have the following results for a broad general class of equations in the different function space we introduced previously, defined by Weinan and his collaborators. So in the previous two results, I defined this space in the considered spectrum bound space. But you can actually set out the equation in the integral form bound space, or bound space based on integral formulation. So I will state the result in an informal way. So basically, you have the equation. We have an elliptic PDE defined on whole space. Okay, the general elliptic PDEs on the whole space, with A is a strongly elliptic, and if the coefficients A and the zero term C and the source terms F are all Baron functions in the sense of V9. Okay, in the sense that the function can be written as a integral of the ridge function against the probability measure, then we cannot prove that the solution is another Baron function, but we can prove that the solution can be approximated by another Baron function U, such that the H1 norm between these two functions is less than epsilon. Well, we also have a control on the Baron norm of the function U, and it turns out Baron norm of the function U is bounded by C divided by epsilon, D divided by epsilon to the C times the log 1 of epsilon. Okay, so you can see that given any precision parameter epsilon, the error bound, so the upper bound for the Baron norm of the approximation U, or in other words, it's a complexity of the Baron function, is bounded by D to some constant, right? D to the log 1 of epsilon. So there's no the D does not appear in the exponent of the error estimate. This final Baron norm estimate only involves the polynomial of D. Okay. Moreover, if the Baron space is defined by a cosine activation function, so this previous estimate is for any activation function or any broad class of activation function. But if the Baron space is defined by a cosine activation function, it's actually getting better. So the upper bound can be improved up to D to the C times the log 1 of epsilon. So you can get rid of 1 of epsilon in this upper bound. Okay. Anyway, so this is proved by our recent preprint. This result basically show you that in some cases, in particular for elliptic PDEs, if the coefficients and the right hand side of the equation are not complex enough in the sense that they are all Baron functions, then the solutions are not complex either. So they can be approximated by another Baron function. Okay, remember, Baron function can be well approximated by two linear networks. Okay, so in that sense, for those PDEs, you can effectively using linear networks to approximate them. So that's basically what I want to say. Let me conclude. So we derived some the dimension-free priori generation error estimates for Schrodinger problems on the spectrum bound space. We also established a new regularity theory for the elliptic PDEs in the bound space defined in both spectrum bound space and also the bound space with the integral form. So there are a few interesting future directions. So first, can we establish similar regularity results for a broad class of PDEs? So there's still some ongoing work between I and my collaborator. The certain subtlety in generating the results for other PDEs, in particular for nonlinear PDEs. It's unknown at the moment how to prove a similar regularity estimate in the bound space. And second point, can we develop similar error estimates for other numerical based methods like pins or weak adversarial networks? So basically, these are PDEs, numerical based methods with a different loss functions. Okay, and I have to say that for pins, it's actually quite it's not difficult to extend the result to the pins, but for weak formulation, there's still some open problems on that. And the last point, how to analyze the convergence of the training dynamics. So that's a big open question in this field, and also in general in the machine learning community, because the loss function is usually non-convex. So the potential could be a multiple global minimum. How to get to the global minimum using green descent? It's some challenging question. So this all the results are reported here based on the 3 papers and preprints. So the first one appeared in Codes this year, and the last 2 appear on the archive. So I think I'm going to stop here. Thanks a lot for the attention.
Thank you, Yulong, for a very intriguing talk. Are there any questions from the participant, please?
Maybe I can ask a question. Yeah, thanks for the great talk. I was wondering about these definitions of the norm in terms of the L1, basically, of the Fourier, or kind of, I guess, equivalently of the neural networks. I mean, it of course reminds quite a lot of sparsity, right? So I was wondering whether this idea of having some sort of sparsity appears in the proof, or in the is it a good idea to think about it like this? Sorry,
it's actually a good question. So it's relevant to sparsity because it's L1, right? It's an L1 norm in the definition, and also in the control of the weights. All of them are L1 in some sense. But in the proof, I didn't use any kind of sparsity arguments. I basically as you can see the proof, you will not see any kind of special arguments to deal with sparsity.
So what's then the trick?
But I agree that.
So what's then the trick of using
L1? Say that again?
So what's then the trick of using L1 instead of L2?
So the why the L1 is important here is because you want to write this function indent as an integral of some test function against a probability measure. And it turns out that if this guy is L1, then you can always normalize L1 function as a probability measure, right? So that's why the L1 is important over here.
And then you get this Monte Carlo kind of rate, right? From
yes, exactly. Then you use Monte Carlo to describe this, the test function with a finite sum, and it turns out this guy can be viewed as a 2-layer network.
Okay, that's great. Thanks. Mm-hmm.
Yeah, thanks for the question.
I have a question regarding your regularity result for Schrodinger.
Mm-hmm. Yeah.
So in usual Sobolev framework, there is also this difference of 2 between the exponents on the right-hand side and the left-hand side. But this doesn't hold for non-smooth domains. What is the assumption on the domain omega here?
Oh yes, so here I should say this more specifically. So omega for me is always 0, 1 to the d. It's a hypercube on the dimensional space. So I define it as a beginning.
Okay, right. So
it's a simple domain. Yes.
Okay.
Yeah. It's over here.
Does this theorem also include singular? Oh, it doesn't, because you also have a maximum bound, right? So the singular potentials are not included here.
Oh no, yeah, that's a good question. That's exactly the question I want to study at the moment. For example, for Coulomb kernels, this assumption will not satisfy.
Which one?
For Coulomb kernels or other singular kernels, this will not satisfy. But it's still open question how to get similar results for the regularity.
So in the Sobolev framework, in that case, you need weighted Sobolev spaces.
Yeah, maybe. I'm not sure about the Sobolev case because I'm not familiar with that.
I worked on Sobolev's case for problems with singular. So we did it with in the framework of weighted Sobolev spaces. So probably you will need a weighted Baron spaces here. Just arbitrary guess.
Okay, that's very interesting. Could you send some papers to me?
Yeah, I can get in touch with you.
The links. Okay, thanks. That would be very helpful.
Another sort of question is more practical. So if you go back to approximation result that you have, like purely approximation result in one of the slides before regularity.
Yeah.
Somewhere here. Yeah.
Yeah.
Yeah, things like this. Yeah. So how you go about verifying this result in practice?
What do you mean? How do?
So, for example, you want to set up a numerical experiment that would confirm this result. How would you go about this?
Well, you just increase the number of neurons, right? Number of hidden neurons to see whether you get this kind of weight.
Okay. Have you done this?
Right. We have done numerical experiments for PDEs. You will find that in our. We haven't uploaded this to archive.
No, not for PDEs, just for purely for approximation. It's like you get a function u from your class.
You certainly will find this.
You get you take a function u from your class.
We haven't tested just for. We haven't tested the just approximation. We did this for PDEs. Okay. And we find there's a trade-off, exactly the trade-off between the two parts, the statistical error and approximation error. But somehow our numerical results show that the rates are not optimal. That's consistent to what I just said. The approximation rate may not be optimal. So these two things, right? Approximation error and the statistical error. These two things are competing each other. You can see this exactly from the results, the numerical results, and there's a U shape, a U curve. But the rates is not sharp. Most rates are not sharp from the numerical experiment.
Okay, but when you do numerical experiments, you will have to account for training. For training errors.
For training, yes, but training we just use the standard like optimizer in PyTorch.
Yeah, I know, but this also, well, you probably, when you studied like numerically, you probably set up a neural network with let's say 4 neurons, then 8 neurons and 16 neurons, and you kind of measured convergence, right?
Yes.
But in each run, let's
so
say,
in the
yeah, keep going.
Yeah, I was saying that in the numerical experiments in the U curve, right? You fix the number of sample points, then you plot the curve as a function of m. You will see that the error will first go down and then go up. So this means that these two terms are competing. So the first, as m increases, goes down because the approximation is dominating. But if m is pathing some critical points, which depend on n, then if you further increase m, well, the statistical error will dominate. So this will give you a higher generation error.
Okay. So this like Monte Carlo error competes with the approximation error from the neural network.
Yeah.
Okay.
So that's what we find for Deprived methods. And I have to say that there's a very interesting question in relevant to the well-known phenomenon in the machine learning community. It's called double descent. Well, for some statistical models or machine learning models, you can see if you increase further the complexity of the models, you will decrease the generation error further. But we do not see this in Deprived methods, or Ritz loss. Okay, so if you increase m, the error will always increase. That's what we found in practice. So somehow the double descent will not occur in this setting. At least for Deprived method, it will not occur.
It's
but
interesting.
Maybe this will appear for other neural network-based methods with a different loss function.
It's interesting that your approximation result has only the bound dependent on the number of layers, or number of neurons.
Yeah. That's because, I mean, that's an approximation, right? We didn't make any Monte Carlo error in approximation, right?
But in practice, when you approximate, you need samples of data to train your network, and then this will depend.
Yeah, the sample data is used to compute the energy. Right? The approximation is just for the approximation of the function itself, right? It's not relevant to the energy.
Yeah, maybe. Yeah, maybe I misunderstand something. Yeah. Okay, thank you very much. Thank you.
Thanks for the question.
Yeah, hi, Yulong. I just have a quite simple question here.
Sure.
Yeah, so actually, I think it's related to Alex's question. You just also your discussion is just actually, you just had the discussion you just have. So it's also about the Monte Carlo kind of error. And actually, I'm curious, like how how your theoretical analysis, how your theoretical results depend on the kind of Monte Carlo integration, and in particular, so what if I mean, here you have a high dimensional integration into compute, right? So you use Monte Carlo to compute that. So how, I'm just wondering, what if you are not using Monte Carlo? Say you use sparse grid to compute this integration. Does it change your theoretical results significantly or not?
We haven't used that because sparse grid, I think it still suffers from curse of dimensionality, right? So the error bound.
Yeah, but if we have a trade-off, right? Because and certainly it really depends on exactly how large the dimensionality is. Yeah. So I mean, in certain dimensions, the Monte Carlo method is independent of dimensionality, but it also suffers from very slow convergence.
The constant can be huge as well.
Yeah, I'm just curious. Like, go ahead, please.
I haven't checked that yet. I think. If the dimension is moderate, it's not super high. I think maybe sparse grid is more beneficial, I would say. But if the dimension is really high, so we test the PDEs in defining 200 dimensions. So D is 200 example. In that case, I think the method still work, but error is actually quite big. It's like 50% relative error, so it's quite large. So I think sparse grid, I'm not sure about that, but I think in really high dimensional space, this probably will also give big error. But the goal here, I would say that our focus here is really trying to get a dimension independent convergence rate on the generalization error. So we didn't consider sparse grid because we think Monte Carlo scheme. The statistical error already involves a dimension dependence in the Monte Carlo scheme. So that's why we didn't actually consider a sparse grid method in the analysis.
Yeah, but suppose you use like say sparse grids. I suppose like your convergence results will change. It will in some sense it becomes dimension dependent, right? You will have kind of a dimension parameter in your theoretical results, right?
Yeah, I think so. So that some of the constant will depend on dimension, and the rate may also depend on dimension as well.
Yeah, thanks. Yeah, thank you.
Thanks for the question.
Thank you very much. Do you have any other very quick questions, please?
Maybe I can ask a very quick question.
Yes, please.
So I'm really interested in this numerics and the double descent that you said, right? Can I just ask, like, so sort of numerically, you tested this bound on this slide, right? That you have in like the expectation of the energy, or
and H1 difference.
Because like as far as I understand this double descent, it's sort of it's about generalization, right? So you have some points and you try the solution at a different point that you haven't used for.
Yes, we really compute the expectation using Monte Carlo. We run multiple solutions. So this is U and M based on different samples, right? So you give one set of samples a computer solution, and you change your samples and rerun to get a solution, and you take the average. the computer expectation. Then the error doesn't decrease if you further increase the complexity of a model.
Have you tried the same with pins?
I'm actually trying that with my IU students at the moment.
Because this would be kind of closer, right, in the setting to the double descent theory.
Yes, I agree. That's what I mean. The difference is not really, the Ritz formulation is not the L2, the all this square formulation, right? So it's not typical loss you was using in machine learning. Pins is more close, it's much closer to us, you see.
Right.
Yeah, I haven't got any results from him yet. The student is still working on the experiments.
Yeah, but that's interesting, very interesting. Yeah, thanks.
Thanks for the question.
Okay, I think we already over time. So thank you, Yulong, very much for the very interesting talk that create a lot of interaction with the audience. So we will stop the session today, and maybe Yulong, can you stay a little bit longer for if other person have
sure.
question?
Yeah, I can
Yes.
stay I can stay for like another half an hour if you
Okay.
want to stay longer.
Okay, yeah, thank you very much. So we will stop recording now.